Namaskar everyone. Welcome to this module of water supply, medical gas supply, HVAC and biomedical waste disposal. I am Shruti Nagdeve, a PhD research scholar at School of Planning and Architecture, New Delhi, and I shall take you forward to this module. We start with water supply. Designing a water supply and sanitary system for a hospital is a complex task. Since most of the service lines are concealed, faulty design and installation or any compromise in quality material will lead to problems which may be difficult to rectify later. Defective installation would affect the functioning of the hospital and lead to unhygienic conditions which are not suitable as a function of service. Two important components of the system are water supply distribution network and sewage disposal. The design should allow water recyclation if needed for AC cooling tower or makeup tower. Now, what are the sources of water supply? The primary source of water supply in hospitals is usually public utility supply system. There are other alternative sources such as bore wells, tanker supply, recycled water which will be taken from treated waste water from basin, shower, laundry, etc. and that will be used in WC flushing and landscape areas. As per National Building Code 2016, the minimum water requirement in a hospital which will not have a laundry and kitchen per bed shall be: first, the number of beds that do not exceed 100 in number. The domestic per day liter shall be 230 per head. Flushing per day liter should be 110 per head, and total consumption day liter shall be 340 per head. For beds exceeding 100, it will be 300 per head, 150 per head and 450 per head respectively for the categories as mentioned above. And for outpatient department, it will be 10 per head, 5 per head and 15 per head respectively. Quality of water supply. Eventually, every aspect of operation gets affected if the quality of water supplied is not up to the mark. It is therefore essential that suitable water of microbiological quality is provided for drinking, laboratory procedures and solutions used in medical and surgical treatment. Chemically acceptable water is essentially for the operation of equipment, laboratory tests and dietary purposes. So, to check the quality of any water supply, it is a good practice that a regular surveillance programs should be instituted. This normally includes evaluating the source of supply, equipment and distribution system, and routine microbial and chemical analysis of water. For that, an engineer should have samples of water collected routinely and have them sent for analysis. In addition to the potability of water, water should be tested for hardness and iron. The hard water is detrimental to equipment and may increase the operating cost. A hospital should follow routines in water processing programs that will be including chemical treatment of water, deionization, distillation, filtration and sterilization. Hot water supply. It should be provided in all toilets and wash basins. It is supplied through centrally distribution system and is usually generated using oil-fired hot water generators. The temperature of water ranges between 55 degrees centigrade to 60 degrees centigrade, and it is stored in an insulated closed pressure hot water mixing. So, the best suited location for any boiler, mixing tank and associated pump is a separate pump room or a room adjoining to it. The exhaust flue gases from the hot water boiler should be taken above the building as a statutory regulation and discharged into the atmosphere. The complete hot water system should be distributed to various utility outlets using insulated GI pipes. In order to eliminate any wastages and get immediate hot water supply, a hot water circulation pump is necessary. The hot water pressure in the pipeline should be maintained in the same way as in the cold water supply by connecting the hot water supply to the hydropneumatic systems. Steam. It is one of the necessary requirements in kitchen, laundry, CSSI and other sterilization areas. It is generated at a pressure of 8 to 10 kg per square centimeter with the use of oil-fired steam boilers. There are various areas which require steam at different pressures. Therefore, it is very important that pressure reducing stations with headers should be provided to tap the required steam. We should also take care that the pressure is recovered by condensation and conserved waste heat. The steam boilers should be located next to the hot water boilers. If the steam requirement is not much, it is better to have a combined steam boiler that supplies both steam water and hot water. Now, drainage system. Drainage system of the hospital should be simple, effective, economical and serviceable. It should be designed keeping in view the kind of septic and toxic waste that needs to be effectively disposed of. So, we know that there are various plumbing systems such as one stack system, double stack system. For a hospital, it is advisable that we adopt a double stack system in which a separate stack is provided to collect waste and soil from the toilets and other areas. Pipelines should run with sufficient slopes so that the sewage could be conveyed to inspection chambers by gravity. Drainage system should also have a provision to terminate the collected sewage in municipal sewer line via a battery of inspection chambers or manholes, and where it is not possible to do so, an alternate arrangement like sewage treatment plants should be made. For sewage disposal, it is preferable to use PVC pipes as they are easy to install and repair and also allow for smooth flow of sewage. Sewage treatment plant. The objective of a plant here is to stabilize the decomposable organic matter present in sewage to produce effluents and sludge. These can be then disposed of in the environment without causing any health hazards or nuisance. The treated sewage water can also be reused for various purposes like gardening, landscaping, flushing of WCs, AC cooling towers and many others. Coming to medical gas supply system. A medical gas supply system takes the form of either cylinders or piped gas system depending on the requirement of the hospital. We now discuss the first type, that is cylinders. These are made of thin-walled seamless molybdenum steel in which gases and vapors are stored under pressure. The top end of the cylinder is called neck and this ends in tapered screw thread into which the valve is fixed. The thread is sealed with material that melts if the cylinder is exposed to intense heat. This allows the gas to escape so that there is a reduction in the risk of any explosion thereafter. There is a plastic disc around the neck of the cylinder which marks the year when the cylinder was last examined and then can be identified from the shape and the color of the disc as well. Cylinders are manufactured in different sizes that are from A to J. In an emergency situation where the patient has to be taken from home or during the process of transport, lightweight cylinders come into role. They are made of aluminium alloy with a fiberglass covering epoxy resin matrix. They have a flat base which is helpful during storage and handling in transportation or at home. Now the storage capacity. Oxygen is stored as a gas at a pressure of 13,700 kilopascals. Nitrous oxide is stored in liquid phase with its vapor on top at a pressure of 4,400 kilopascals. As the liquid is less compressible than the gas, this means that the cylinder should be only partially filled. The amount of filling is called the filling ratio. It is the weight of the fluid in the cylinder divided by the weight of water required to fill the cylinder. Partially filling the cylinders with liquid minimizes the risk of dangers. In hotter climates, the filling ratio is 0.67. We now come to medical gas supply system. A medical gas pipeline system is installed to provide a safe, convenient and cost-effectively system for the provision of medical gases to the clinical and nursing staff at the point of use. It reduces the problem associated with the use of gas cylinders such as safety, porterage, storage and noise. It is a system where gases are delivered from centrally supplied points to different sites in the hospital at a pressure of about 400 kilopascals. Special outlet valves supply the various needs throughout the hospital. Oxygen, nitrous oxide, Entonox, compressed air and medical vacuum are commonly supplied through the pipeline system. The components of a medical gas supply system are Central supply points such as cylinders, cylinder banks or liquid oxygen storage tank. Pipework made of special high quality copper alloy which both prevents the degradation of the gases it contains and has bacteriostatic properties, and the fittings used are made from brass and braced rather than soldered. The size of the pipe differs according to the demand that they carry. Pipes with a 42 mm diameter are usually used for leaving the manifold. Smaller diameter tubes such as 15 mm are used after repeated branching. Outlets which are identified by gas color coding, gas names and by shape. They accept matching quick connect, disconnect, probes, Schrader shocks with an index collar specific for each gas or gaseous mixture. Outlets can be installed as flush fitting units, surface fitting units on booms or pendants suspended on a hose and gang mounted. Flexible color coded hoses connect the outlets to the anesthetic machine. The anesthetic machine end should be permanently fixed using a nut and liner union where the thread is gas specific and non-interchangeable. Isolating walls behind break glass covers are positioned at strategic points throughout the pipeline network. They are also known as area valve service units. Sources of supply for pipeline installations. First is oxygen. Oxygen is generally supplied from a liquid source such as large vacuum insulated evaporator or a liquid cylinder or compressed gas cylinder or a combination of these to provide the necessary standby backup capacity. Oxygen can also be supplied from an oxygen concentrator. Such systems are usually installed where liquid or cylinders are expensive, unavailable or impractical. Medical air is usually supplied from a compressed air plant that includes high quality drying and filtration equipment. Blending oxygen and nitrogen on site to provide a high quality product with minimum maintenance can also provide medical air. Where such systems are installed to provide both oxygen and medical air, nitrogen can be used for power source for surgical tools. All other gases are supplied from cylinders. Now, what are the basic principles of design? A patient safety is paramount in design, installation, commissioning and operation of any medical gas pipeline system. The basic principle of safety are achieved by ensuring quantity of supply, identity of supply, continuity of supply and quality of supply. We shall discuss this in depth in the coming slide. Quantity of supply. This is achieved by ensuring that the design of the pipeline installation and capacity of the supply plant is sufficient to provide the required flows of gases and vacuum for the intended number of patients to be treated at any time, and adequacy of supply is established during commissioning of the systems. Identity of supply. This is achieved by ensuring that all points to which the user can connect medical equipment and user replaceable components are provided with gas specific connectors. Such connectors are also identified by symbol and often color. The gas specificity is maintained by comprehensive tests and check during installation and commissioning and during any work or maintenance on the system. Continuity of supply. This is achieved by installing as a minimum duplicate components and providing additional means of supply provisions in the event of failure of the primary and secondary plant or supply system. Systems are also connected to the essential electric supply. Quality of supply is ensured by the use of gaseous or liquid sources that are provided to an appropriate product specification. In case of compressor based systems, filtration equipment to a known and agreed standard is installed. To ensure that the product is not adulterated in the distribution system, pipeline installations and components are required to meet agreed specifications. Uses of gas and pipeline installations. Oxygen. It is one of the most extensively used gases for respiratory therapy and life support and is additionally used in anesthetic procedures. Medical air is mainly used in respiratory therapy as a power source for patient ventilators and for blending with oxygen. It is also used as driving gas for nebulized drugs and chemotherapy agents. Surgical air is also used at a higher pressure to power a variety of surgical tools and other devices such as tourniquets. Nitrous oxide is used for analgesic purposes and anesthetic purposes, being mixed with air, oxygen and nebulized agents. Pipeline system for a 50% mixture of oxygen and nitrous oxide are widely installed for analgesic purposes, particularly in maternity departments. Helium-oxygen mixture is used to treat patients with respiratory or airway obstruction and to relieve symptoms and signs of respiratory distress. Carbon dioxide is used less commonly now as a respiratory stimulant and for insufflation during surgery. Piped vacuum is provided in most clinical areas by means of centrally sited vacuum pumps. Now, what are the quality requirements for medical gases and air? Medical gases supplied from cylinder or liquid sources comply with appropriate section of the medical standards. The quality specification for medical, surgical and synthetic air and oxygen enriched air produced from a pressure swing adsorber system is given in the table. The medical air and synthetic air should be comply with medical standards. The quality of pipe medical compressed air and the particular content, dryness and concentration of impurities should comply with the requirements for maximum concentration given in the table. Bacteria filters should be included in medical and surgical compressor systems to reduce the risk of delivering spores or other infectious materials to vulnerable patients. Microorganisms can penetrate a bacteria filter if the material is wet. Therefore, it is essential that the dryness of the medical air supplied to a bacteria filter is checked regularly and at least at 3 months at the test point using testing equipment. Now, what are the sources of gases supply? The source of gas supply can be cylinder manifolds and in the case of oxygen, a liquid oxygen storage tank or oxygen concentrator. What are the components? A large cylinder, example a size J with 6,800 liters capacity. These are usually divided into groups, primary and secondary. The two groups alternate in supplying the pipelines. The number of cylinders depend on the expected demand. All cylinders in each group are connected through a non-return valves to a common pipe. This in turn is connected to the pipeline through pressure regulators. Liquid oxygen, a vacuum insulated evaporator as shown in the figure, is the most economical way to store and supply oxygen. The components here are a thermally insulated double-walled steel tank with a layer of perlite in a vacuum is used as insulation. A pressure regulator allows gas to enter the pipeline and maintain the pressure through the pipeline for about 400 kilopascals. A safety valve opens at 1700 kilopascals, allowing the gas to escape when there is a buildup of pressure within the vessel. This can be caused by under demand for oxygen. A control valve opens when there is an excessive demand on the system. This allows liquid oxygen to evaporate by passing through superheaters made of uninsulated coils of copper tubing. Oxygen concentrators are other type which extract oxygen from air by different absorption. These devices may be small, designed to supply oxygen to a single patient, or they can be large enough to supply oxygen for a medical supply gas system. Entonox, this is a compressed gas mixture containing 50% of oxygen and 50% of nitrous oxide by volume. It is commonly used in casualty and labor ward setting to provide analgesia. A two-stage pressure demand regulator is attached to the Entonox cylinder when in use. As the patient inspires through the mask or mouth, gas flow is allowed to occur. Gas flow ceases at the end of an inspiratory effort. Entonox is compressed into a cylinder to a pressure of 13,700 pascals. If the temperature of the cylinder is decreased below 5.5 degrees centigrade, liquefaction and separation of the two components occur. This results in compressed air. Medical air is supplied in a hospital for clinical uses or to drive power tools. The former is supplied at a pressure of 400 kilopascal and the latter at 700 kilopascal. The anesthetic machines and most intensive care ventilator blenders accept a 400 kilopascal supply. The terminal outlets of the two pressures are different to prevent misconnections. Air may be supplied from cylinder manifolds or more economically from a compressor. Oil-free medical air is cleaned by filters and separators and then dried before use. Centralized vacuum system. This system consists of a pump, receiver and a filter. The pump is capable of creating a negative pressure of -53 kPa and can accommodate an airflow of 40 liters per minute. It is recommended that there are at least 2 vacuum outlets per operating theatre, 1 per anesthetic room and 1 per recovery bed. Now coming to the design criteria of HVAC. We start with operating rooms. The objectives of air conditioning in any operating room is 1. To introduce uncontaminated fresh air, dehumidified air and a cool air. The second is to exhaust the air contaminated during surgery. Third is to provide working comfort for the surgical team and then prevent contamination from adjacent areas. Some of the design parameters considered for operating rooms are: the temperature range should be in between 23 degrees Celsius to 24 degrees Celsius. Positive pressure to be maintained with respect to adjacent areas. Criteria of design of an HVAC in a labor delivery suite. Unlike the surgery, the labor delivery suites operate on a 24-hour schedule. These suites are air conditioned at the same temperature as the operating rooms, which is usually 23 degrees centigrade. Even in hospitals that are not centrally air conditioned, labor delivery suites are one of the areas that generally are air conditioned. The nurseries are one of the important areas in the maternity department which requires air conditioning. Design criteria for morgue and autopsy rooms. As the morgue is generally designed to hold bodies in refrigerated body boxes, it poses no particular air problem. However, the autopsy rooms have odor problems. A large air supply and an exhaust system should be provided. The exhaust should be carried above the roof, if possible out of the building site area. The objective of air conditioning the autopsy room is to provide comfortable working conditions for doctors and other personnel. The air pressure in the autopsy rooms should be negative compared to the adjacent areas to overcome odor. Design criteria for central sterilization and supply department. In a modern CSSD, the decontaminating area and sterilizing area and the sterile storage rooms are physically separated. The sterilizing room generates a great amount of heat and working in that condition is difficult. Special precautions should be taken regarding air conditioning and ventilation if the sterilization work uses ethylene oxide. In many hospitals, the CSSD is a part of operating rooms. If a operating complex is air conditioning, it is but natural that the CSSD will also be air conditioned. Due to the constant working of washer, sterilizers and equipments, this place usually stays warm and heat is continuously generated. For that reason, HVAC in this area and to provide cooling for conditioning is very essential. Design criteria of HVAC for equipment rooms. Places such as radiology suite and catheterization lab that houses sophisticated and sensitive equipments like the CT scan and MRI should also be air conditioned. These pieces of medical equipments are very sensitive to large deflections in temperature and humidity. Thus, special care should be taken to control these two factors. The general areas. The corridors should have adequate ventilation. Individual private rooms should be independent fan coil unit and thermostatic control for flexibility. All toilets should be exhausted for odor with centrally exhaust system. Now come to the next segment, which is biomedical waste management. It is defined as any waste which is generated during the diagnosis, treatment or immunization of human beings, animals or in research activities pertaining thereto or in the production or testing of biological. There are three types of biomedical waste. First is hospital waste. It refers to all waste, biological or non-biological, that is discarded and are not intended for further use. Biomedical waste, it is any waste which is generated during the diagnosis, treatment or immunization of human being or animals or in research activities pertaining to these kind of testing and biologicals, and including categories mentioned in Schedule 1. Third category is infectious waste. The waste which contains pathogens in sufficient concentration or quantity that could cause diseases. It is hazardous, that is cultural and stocks of infectious agents from laboratories, waste from surgery, waste from originating from infectious patients. Biomedical waste is categorized into two divisions of hazardous and non-hazardous waste. Hazardous comprises of 10 to 25% of waste, which is further categorized as infectious waste, approximately 15 to 18%, such as non-sharps, sharps, plastic disposables, liquid wastes, and other such radioactive discarded glass, pressurized containers and chemical waste are of approximately 5 to 7%. The Ministry of Environment and Forest in 1986 passed this act and notified the biomedical waste rules in July 1998. As per the rule, it will be the duty of every occupier, that is person who has the control over the institution or its premises, to take all steps to ensure that waste generated is handled without any adverse effect to human health and environment. Categories of biomedical waste. There are 10 categories which define the wastes and the treatment and disposal for each waste category. The first one, human anatomical waste, which is treated by incineration and deep burial. The second one is animal waste. Again, the treatment procedure is incineration and deep burial. Third category is of microbiology and biotechnology waste. These are treated by local autoclaving or microwaving. Category 4 are of waste sharps. These are treated by chemical disinfection, autoclaving and mutilation and shredding. Category 5 is of discarded medicines and cytotoxic drugs. This is again treated by incineration or disposal in secured landfills. Category 6 is of solid waste contaminated with body fluids. This is treated through incineration or autoclaving. Category 7 is of solid waste with disposable items, and that can be treated through chemical disinfection or microwaving. The 8th category is of liquid wastes, which is treated by chemical disinfection and discharge into drains. Category 9 is of incineration ashes, and here the disposal is made in municipal landfills. Category 10 is chemical waste, and the treatment is chemical treatment discharged into drains or into secured landfills. Color coding of biomedical waste. So there are 4 colors according to each category. The first color is yellow, which is for waste categories 1, 2, 3 and 6. Here the wastes are human tissue, placenta, organs, body parts from operation theatre, amputated limb and soiled cotton, pad, dressings, all used masks, gloves, plastic apron, head cap and etc. The red color coding is for all infected plastic and rubber items, IV sets, IV bottles, syringes, all tubings, catheter, suction catheter, etc. The blue color category is for waste category 4 and 7. All sharp items, hypodermic needle, scalpel blade and glass cause puncture. The black color is for waste category 5, 9 and 10, solid. The wastes are all non-infection waste, kitchen waste, all cover, wrapper, paper and empty boxes and office wastes. These are the color codings. As you can see, yellow, red, blue and black according to the waste categories as already discussed ago. Now what are the sources of biomedical waste? They can be hospitals, nursing homes, clinics, medical laboratories, blood banks, mortuaries, medical research and training centers, biotechnological institution, production units, animal houses, and such waste can also be generated at home if health care is being provided there. There are certain steps for waste management. The first one is segregation. Second is collection and storage, followed by transportation, and the last one is treatment and disposal. Transportation and storage of biomedical wastes. The waste may be temporarily stored at the central storage area of hospital, and from there it may be sent in bulk to site of final disposal once or twice a day depending upon the quantum of waste. During transportation, there are certain points that should be taken care of. First is to ensure that the waste bags containers are properly sealed and labeled. Manual handling of waste bags should be minimized to reduce the risk of needle prick, injury or any infection. Biomedical waste should be kept only in a specified storage area, and after the removal of bag, clean containers including the lid with an appropriate disinfectant. The waste bags and containers should be removed daily from wards, OPDs or even more frequently if needed. Waste bags should be transported in a covered wheeled containers or large bins in covered trolleys. No untreated biomedical waste shall be kept stored beyond a period of 48 hours. Transportation from healthcare establishment to the site of final disposal in a closed motor vehicle is desirable, as it prevents spillage of waste on the way. Vehicles used for transport of biomedical waste must have the biohazard symbol, and these vehicles should not be used for any other purposes. Deep burial, the category 1 and 2 only in cities having less than 5 lakh population and rural areas. Shredding, the plastic IV bottles, IV sets, syringes, catheters, sharp needles should be shredded, but only after chemical treatment, microwaving or autoclaving. Needle destroyers can be used for disposal of needles directly without chemical treatment. Land disposal, open dumps, secured sanitary landfill, the incinerator ash, discarded medicines, cytotoxic substances and solid chemical waste should be treated by this option. Incineration, it is a high temperature dry oxidation process which reduces organic and combustible waste into inorganic and incombustible matter, usually used for the waste that cannot be reused, recycled or disposed of in a landfill site. The incinerator should be installed and made of operational as per the specifications under the Biomedical Waste Rules in 1998. Certification may be taken from Central Pollution Control Board or State Pollution Control Board. Category 1, 2, 3, 5 and 6 wastes can be incinerated. The wastes which should not be incinerated are pressurized gas containers, large amount of reactive chemical wastes, silver salts and photographic or radiographic wastes, halogenated plastics such as PVC, waste with high mercury or cadmium content such as broken thermometers, used batteries, sealed ampules or ampules containing heavy metals. We have now come to the end of this module. If you may have any questions regarding the hospital services, we are happy to answer them in the question and answer session. Thank you.